morning, dear students. Today we are going to see the practical to determine pKa of acetic acid. First, we need to understand what is pKa. pKa value we usually used to indicate the strength of an acid. Okay, how it indicates the strength of an acid? It is inversely related to the strength of the acid. If pKa value is high, then the acid will be a weak acid. Clear? So, pKa is the negative log of the acid dissociation constant or Ka value. Ka otherwise called the acid dissociation constant. What you understand from that? That means whenever the pKa is high, then the dissociation rate will be less. That means that acid is a weak acid. Then there is a chance to have a doubt there. What is the difference between weak acid and strong acid? If an acid is a strong acid, then it can ionize completely in an aqueous solution by losing one proton. That is the nature of strong acid. Okay, coming to here, if pKa, I will write here, pKa, pKa is high, that indicates that the dissociation ability or dissociation rate of acid is low. That means it is a weak acid. Okay, that is the relevance of pKa. Then next slide, we are going to understand the principle of this practical. In this practical, we are noting on the pH in every discrete points of titration of acetic acid using NaOH. So, how that pH is relating with the pKa? It is related through Henderson-Hasselbalch equation. What is that equation? That equation is pH is equal to pKa plus log of conjugate concentration log concentration of conjugate base by concentration of weak acid. This is the equation. That equation we can write again in this form. pH is equal to pKa plus log concentration of conjugated base by the concentration of weak acid. Okay. Then as we add a base to an acid at a particular point, a neutralization will happen. That means the number of H plus become less than that of number of OH minus. That means its acidity get reduced. Clear? Okay. That is the end point. That is why at the end point the solution change its color. That change in color is a pale pink color. That is the end point. It is clear. So from that end point towards the halfway of titration. Suppose as we start the titration from here and towards a particular point, but after adding a particular amount of that base to the acid, we will get the end point. That's the pale pink color. So a halfway between this, at this point, the concentration of H plus and OH minus will be same at the halfway before the end point. Okay. Then If we consider this equation, as the numerator and denominator got the same value, we can cancel each other, and then the equation become pH is equal to pKa. That means a halfway before the end point, at that point, that pH is equal to pKa. So, for understanding the pKa of an acid, we only need to note the pH at that particular point. But at that particular volume of the base that we added at that point. Okay, at that point, what pH we got, that will be its pKa. Clear? Okay, and if we write this equation in terms using in terms of K, that is the dissociation constant, then we can write that equation again in this form. pK is equal to minus log of Ka, dissociation constant. That is, again it means that it is a relation showing the inverse relationship of a dissociation constant with the pK. This is the principle of this experiment. Okay. So next we can do the practical. Let me see the procedure. Before that, what are the materials required for this practical? Are, let's see that. Materials required are acetic acid 0.1 mole per liter, and NaOH 0.1 normal, burette, pipette, beaker, and phenolphthalein indicator. Okay, let's do the practical. Here we have taken 20 ml acetic acid solution, and I am going to keep this under the electrode of pH meter, which is already calibrated against standard pH of 7 and 4. So after dipping the electrode properly in the solution, we need to add 1 or 2 drops of phenolphthalein to get the end point. So after that, we are starting the titration by adding, not a titration, we are just going to add 2 ml of NaOH, and after adding that much amount of NaOH, we need to stir it. We need to stir it, and need to wait for a while to get a steady value in the pH meter. So we need to continue the same process repeatedly until get a steady, until get a sudden shoot up in the value in the pH along with the end point. Till to that time we need to continue this adding of NaOH and stirring and noting the value of pH. The same thing, again adding, then stirring, noting the pH. We have to note down all the values correctly in a notebook. Then only after finishing this titration, we can plot a graph using the different pH value noted against specific addition of NaOH. Yes, now we can see a shoot up in the value of pH that is showing in the pH meter. On getting that shoot up, we need to wait for a while to obtain somewhat a steady value. On getting that steady value, we can stop adding further NaOH. Next, we are going to find out the pKa of acetic acid using the data that we got through titration. And here we can see the amount of NaOH we have added throughout the titration. It is a multiples of 2. And against that we can see the pH that we noted after each specific addition of NaOH. And using this data we have plotted a graph, and we understood that at half equivalence point, that means from the beginning of titration towards the midway, towards the mid of the titration, then the pH is equal to pKa. At that point, the pH we got is the same as that of its pKa. So here we have added 30 ml. So its half means 15. As we add multiples of 2, we can't find 15 specifically here. For finding the pH at 15, we need to find the average of these two values. 4.7 plus 4.82 divided by 2. Then by that way, we will get the pH at 15 ml of 15 ml of NaOH, that is 4.76, and that will be the pKa of acetic acid. In this way, we can find the pKa. Okay, with this we finish today's practical. Thank you.
I'm an icon, man. My girl about a 10. I should fuck her in a